Hi everyone. This is the first lecture on multi-electron systems. Here we will discuss the general problem of electron-electron interactions and the method for addressing electron-electron correlation in the context of molecules. So let's consider a two-electron system which has stationary nuclei. The Hamiltonian for such a system can be given as the sum of the kinetic energies of the two electrons plus the sum of the potential energies of the two electrons in the field of stationary nuclei plus the interaction potential between the two electrons. Now V12, that is the interaction potential, is a function of R12, which is the vector connecting the two electrons, which in other words is the electronic smear distance. The Hamiltonian is going to be a function of electron density, since V12 represents the electron-electron interaction. Now electrons are quantum particles. The interaction between the smears can be used to find V12. And to get the smears, one can use the probability density of the electronic position. To get the probability density, what we can do is find the squared value of the absolute value of the wave function. But in order to get psi, we need the Hamiltonian. Which brings us to a catch-22 situation, where in order to construct the Hamiltonian, you require the Hamiltonian itself. I would really love that idea on a t-shirt, and I suspect it's because it alludes to the idea that to get something, you need to have it in the first place. Now, let us consider a two-electron system with stationary nuclei, but we impose the condition that the electrons are non-interacting. And the Hamiltonian for such a system becomes simplified, and what it becomes is the sum of the kinetic energies of the two electrons plus the sum of the potential energies of the two electrons in the presence of stationary nuclei. Regrouping the terms, what we can do is to construct component Hamiltonians that take care of electron 1 and electron 2 separately. Now, the eigenfunctions for the non-interacting Hamiltonian are going to be of the form of the product of the individual eigenfunctions of the component Hamiltonians, that is of the form of psi1 times psi2. To see why that is the case, we can operate the non-interacting Hamiltonian on psi1 times psi2. Since the first component Hamiltonian is only going to apply on psi1 because it only has the variables pertaining to the first electron. What we get is E1 times psi1 psi2. That is the eigenvalue times psi1 times psi2. Similarly, the second component Hamiltonian is only going to operate on psi2, and we get E2 times psi1 psi2. Collecting the like terms, what we get is E1 plus E2 times psi1 psi2. And we see that the eigenfunctions are a form of the eigenfunctions of the two component Hamiltonians, and we take the product. One thing to note here is that the eigenvalues are of the form of the eigenvalues of the individual component Hamiltonians taken as a sum. In this case, that is E1 plus E2. Now, when we had a non-interacting Hamiltonian, what we could do is to separate it into two components. And what we were essentially doing is separating the variables. So H1 only has variables pertaining to the first electron, and H2 has variables pertaining to the second electron. However, if the electrons are interacting, this trick is not possible, and the Hamiltonian is not variable separable anymore. This is because we'll have a third term if we had an equal sign. We would have these two terms plus a third term H1, 2. Meaning that the third part of the Hamiltonian takes care of the interaction between the two electrons. Hence, it has variables from the first electron as well as the second electron. Which renders the Hamiltonian variable inseparable. Now, the question arises, how do we go about finding the eigenfunctions for an interacting Hamiltonian? So what we follow is the SCF method, which is the self-consistent field method. It is an iterative method in which the first iteration involves the assumption that the system is non-interactive, and the wave function is given as we saw earlier. The wave function for the system is given as a product of the individual eigenfunctions of the component Hamiltonians, or in other words, the Hamiltonians whose variables have been separated. Now, in the second iteration, what we do is we construct V12, that is the interaction part of the Hamiltonian, using the wave functions we obtained in the previous step, and we add that term to our Hamiltonian and we solve the Hamiltonian to get a new wave function for the system, and we repeat this process until the eigenfunctions that were used to construct the Hamiltonian become eigenfunctions of the Hamiltonian itself. That is, until convergence, and this gives us the self-consistent field method. Now, when we first started talking about multi-electron systems, we talked about R12, which is the vector connecting two electrons. Now the fact here is that electrons are quantum particles, and if they were classical, an analogy to draw here would be that they would be blueberries. But electrons are quantum particles, and the more appropriate way of representing them within our analogy would be to consider a smear formed by a squashed blueberry. Now consider a blueberry that has been placed at the origin of the Cartesian axis, and this would be our analogy for an electron. In this case, it would be a classical electron. But since that is not the case, we squash it and we spread the smear uniformly across the three axes. A natural question to ask here would be, where is the blueberry? Or within the context of analogy, where's the electron? Now, an answer to that question would be, the electron is everywhere. But what we can actually find is the probability of finding the electron in unit volume given a distance from the origin, and this is given as the absolute value of the wave function squared absolute value of the wave function. Now, let's say we have two electrons, classical for now, represented by two different fruits, one a blueberry, one a mulberry. We squashed them both to impose the rules of quantum mechanics and again ask the question, where are the electrons? And again the answer would be they are everywhere. But what we can actually find is the probability of the first electron being at a distance r1 from the origin and the second electron being at a distance r2 from the origin, or the first electron being the vector r1 from the origin and the second electron being the vector r2 from the origin. And this probability would be given as a product of the individual probabilities of finding electrons at r1 and r2 respectively if the electrons were non-interacting. So non-interacting means that the movement of the electrons has no effect on each other, meaning that the first electron does not influence the movement of the second electron, and the second electron does not influence the movement of the first electron, which in turn means that electronic movement is independent of each other. Now, the probability of two individual events happening in succession is given as a product of the individual probabilities, which in this case would be the product of the two individual probabilities of finding an electron at r1, the first electron at r1 and the second electron at r2. Now the probability can be given as the absolute squared value of psi1 times the absolute squared value of psi2, and which in turn is nothing but the absolute squared value of psi1 times psi2, which means that psi1 times psi2 is which also shows that psi1 times psi2 is the wave function for the system if the system is non-interacting. Now let's assume the system is interacting and the probability is no longer the product of the individual probability density. And it's no longer the product of the individual probabilities. And since the movement is not independent anymore, the probability is not a product of the individual probabilities. And This is also the case because the first one can also think about it in this way, that the first electron can no longer be represented by psi1, and the second electron can no longer be represented by psi2, since the electrons are interacting in our case, and psi1 and psi2 are non-interacting wave functions. So what we have learned here is that when electrons are interacting, we can't separate the wave function into a product of the individual component Hamiltonians composed of the different variables. And we need to use different methods such as self-consistent field to address them, and that shall be the subject of discussion in the coming lectures. Thank you.